Hey everyone, this is Hariharan from DSC Cybersecurity Cluster. And as we promised, we further extend our sessions to particular domains now. This will be on reverse engineering. In a CTF, it is hard but yet a thrilling domain to master. Now let me give a quick intro on what reverse engineering is. So grab a notebook and let's get started. Okay, so what is reverse engineering? In layman terms, this could be tearing apart a product to understand how it functions. But coming to cybersecurity, this could mean different things. This could be tearing up a code written in any language to see how it functions with respect to computers. But reverse engineering can also be used to find bugs, vulnerabilities in codes, and can be used in malware analysis and finding viruses even. Interesting, right? Now let's quickly have a look at the agenda. To master reverse engineering, you need to understand how CPU functions. Then we will see examples related to reverse engineering. What is an instruction? There are commands which CPU can understand. But what about us as a reverse engineer? Can we understand it? Yes. Now CPU has its own instruction set architecture, also known as ISA. And examples of instructions will be moving a data between registers and even working with memory. Machine codes. Now these are the codes which CPU directly processes. An assembly language you can see in the picture gets converted into a machine code by an assembler. Each instruction is usually encoded into several bytes. But what about assembly language now? These are mnemonic codes which you will be seeing in a while, but then obviously a low-level language. Now we will see a picture on the language and hardware to understand more about it. You can see C, Pascal on the top, and below you can see a high-level language. This could be your Python. Then you will have your assembly language. Again, it's a low-level language. Then it gets converted into machine code, and finally that's something which hardware understands in the end. Now what about registers? In terms of computer architecture. But then you need to understand these are just temporary variables, like kept in your computer for usage. But then where? Each CPU has a set of registers, fixed registers called general purpose registers. Aha, there we go. You have an overview of all the registers. Now you can see the instruction register, program counter, processor status registers, and of course your GPR, also known as general purpose registers, along with a RAM in this picture. Interesting. Congrats if you have made it this far. I know I get it after all I've done this topic as well. But wait, let's get to the stuff which is coming up. You will eventually understand all the technical jargons. Now let's start with the basics. Yeah, it might be very basic, but will be useful for many people out there. The simplest possible function with a constant return value. Also, don't care about the int main for a while. We will come to that part. Note that we will be seeing an assembly code for an x86 architecture. I have included a bonus section where other architectures has been explained. It will be at the end of the video. For now, let's keep things simple and cool. The assembly output, f with a colon indicating that this is the name of the function. Down you have move EAX123 and ret. What do they mean? EAX register is particularly used for storing the return value. Is it only used for that? Definitely not. It has many uses, which we will be looking at the upcoming sessions. The ret is a keyword for return execution to the caller, and move, you might have guessed it, does the assigning job, which is EAX equal to 123. Very easy, right? Okay, so this is programmer's favorite word, hello world. Again, a simple int main function, so it should have a return value at the end. This function prints hello world, and then the cursor points to the next line. Can you pause the video and guess the assembly output if you can? Congrats if you got the output. Definitely you're a genius. But anyways, let's see the code. You can see the code is very huge. And also note that we use the GCC compiled work here. We have other compilers which gives different output, but almost the same as this. I have pushed that to the bonus section as well. Note this code down and we will be breaking the code in a bit. Yeah, I get it, but trust me, you'll get used to the technical jargons very soon. This particular instruction right here is a main part of our code. The address of hello world string is located in the EAX register first. Then it is saved onto the stack. Again, stack is a temporary place where your variables and its values sit. This instruction is kinda special. It aligns the ESP register's value on a 16-bit boundary. All the values on a stack get aligned the same way. But why are we doing this? The CPU performs better if the values are located in the memory at addresses aligned on a 4-bit or a 16-bit boundary. These are some things you need to remember because you can see them in every assembly code. Now things get more simpler here. This instruction seems unnecessary, but it allocates 16 bytes on the stack. But only 4 are necessary, right? Why are we doing this? This is because the size of the allocated stack is also aligned on a 16-bit boundary. I hope it's clear now. Let's move forward with the next slide. This slide is fairly easy to understand. The printf function is being called with the instruction _printf. Also remember, we altered the value of EBP and ESP, which stands for base pointer and stack pointer respectively. The leave instruction sets the stack pointer ESP back and restores the EBP register to its initial state. Now EBP, again stands for base pointer, also is known as frame pointer, is used in the entry to your function and it pushes it to the state of the value for calling the function. What next? Nothing. We have completed about 0.1% of reverse engineering. But progress is progress, right? Next is a bonus section which contains the code compiled in different architectures and compilers. This is the bonus section I was talking about. Here I'm just going to show you the outputs of different compilers and architectures. Remember we took example 1. Now there is MIPS and ARC code here. These are architectures like x86. Now I would like you to do a quick search on ARM and MIPS cheat sheet. I'm not going to explain this, but instead I want you to do the part of learning. If you have doubts, you're free to comment down and I'll reply to your doubts. This was your example 2, a program to show all compiler output now. I'm going to show about 6 different outputs to you now. Again, I'll be just showing them but won't be explaining the part. I want you to learn. This is a very good technique to solve different CTFs too. This is the x86 MSVC 2010 compiled work. And there is this, the continuation part to it. You can see it's almost similar to the one which you saw before. The same concepts has been used here. This is the x86 GCC compiled work. This is the one which I explained before. This is the GCC compiled work, which is AT and T syntax. And this is a continuation to it. Now moving on to x86 64. Again it's the same architecture almost, but then you have some differences here. This is again the MSVC compiled one. And this is the GCC part of it. So I think I've explained, which is really good for the first session. I'll see you soon in the next sessions, upcoming sessions, which we will be solving real questions, and we'll also be learning more on reverse engineering in the next upcoming sessions. Thank you.